Hi folks, we're going to take a look at a fairly common analytic geometry problem, and that's the idea of finding the distance from a point to a line. So if you read the description here as to how we do that, well, we have some point. In this case here, it's the point 619, okay, and we're finding the distance to some given line. And the way we define that is it's the line segment that joins the point to the line in such a way that it creates a 90-degree angle. And the reason why we choose that is because this is the distance that's going to have the smallest value. So if you take any other distance, okay, you can sort of see that by thinking about Pythagoras. If you make any other distance, it's always going to be smaller than that length there, okay, because that'll be like the hypotenuse of a right angle triangle. Okay, so this is how we define the distance between the point and the line. Now, hopefully you thought about this, maybe even solved it and saw that this was very, very similar. In fact, almost exactly the same problem as finding the altitude of a triangle. Okay, so let's go ahead and see how we solve this. The other thing I would like to mention is notice how my diagram, I make no effort to necessarily make it accurate because I'm just using the diagram as a guide. Okay, I'm not actually going to be measuring anything later on to check my answer. Okay, so it saves me time from having to draw a Cartesian plane and figure out the line precisely. Okay, and the line here is x minus 2y equals -8. So if we want to find the length of this line segment, well, we need not just one point, we also need the other endpoint. So our goal is to determine this point of intersection. Sorry about that. So how are we going to do that? Well, we've got a point of intersection of two lines. So we're going to have to determine the equation of each of these lines and then solve a system of equations to find the point of intersection. Now we're already given the equation of one line. We need to find the equation of this second line, which is perpendicular. And that's where we're going to start. This line is perpendicular to that one, so that allows us to find the slope of the second line. And we have a point that this second line has to pass through, and so we have enough information to find the equation. Okay, so let's start by finding the slope of our first line here, and so I'm going to rearrange this so that it's in the form y equals mx plus b. So we've got x minus 2y equals -8. So I'm going to move the -2y to the other side of the equation, but I'm going to write it on the left. Okay, and so I'm moving the -8 to the other side, so it's going to be equal to x plus 8. And now just divide both sides by 2, so we have 1/2 x plus 8 divided by 2 is 4. So now we know that the slope is just 1/2, and so we need the perpendicular slope in order to find the equation of the other line, which is the negative reciprocal, so -2/1 or -2. So now I can find the equation of a line using my slope-intercept form. So I can input the y value of a point on the line, so 19 equals the slope -2 times the x value of a point on the line, which is 6 plus b. So we have here -12 plus b, so the b value is just going to be 19 plus 12, so 19, 29, 31. Okay, so that means the equation of my perpendicular line is y equals -2x plus 31. But what we have is a system of equations. Okay, we have this first line here, the one that's given, and now we've got the second line, the one that we just determined, and we have to solve this system to find the point of intersection. Now, often you see me using elimination. I'll use substitution here since they're already both isolated. So what I'm going to do is I'm going to substitute this y with 1/2 x plus 4 because it's also equal to y. Okay, so we can write the equation 1/2 x plus 4 equals -2x plus 31. And as we want with system of equations is now we're solving something with only one variable. Now, instead of working with the fraction, I'm going to use that trick of just eliminating all denominators. So I need to multiply by the lowest common denominator. 2 is the only denominator, so I'm going to multiply both sides by 2. Okay, and what do we have? Well, we have 2 times 1/2, which is 1. So just x plus 2 times 4 is 8. And then on the other hand side, we've got 2 times negative 2, negative 4x, and then 2 times 31 is plus 62. Okay, I'll bring all the x's to the left side. So x plus 4x is going to give me 5x. And then here, 62 minus 8 is going to be 54. Okay, so I need to divide both sides by 5. But I suspect that's going to be a nice decimal. So remember, any decimals that are finite decimals, we don't have to leave in fraction form. So 54 divided by 5 is equal to 10.8. Yeah, it's a nice decimal. Okay, and now let's find the y value. So I'll use this equation here so I don't have to deal with the fraction. So the y value would just be negative 2 times the x value I just found, 10.8 plus 31. Okay, so again, let's take out the trusty calculator. I already have the 10.8 there. So times negative 2 and then plus 31. And we have 9.4. Okay, so I'm going to move up to this other column here. So now we have that our point of intersection is equal to x was 10.8 and y was 9.4. Okay, and so now we found that thing that we needed, the point of intersection, because now I have the given point of 619, and so the distance is just defined as the distance between these 2 points. So we'll use our distance formula. So we have distance is equal to square root of, well, the difference in the x's squared, so 10.8 minus 6 all squared, and then we add the differences in the y's squared, so 9.4 minus 19 all squared. Okay, and then from there we'll simplify this. Now, because this is just a straightforward math problem, just find the distance between a point and a line, I'm going to expect an exact answer at the end. But if this was figuring out, the distance of a road that connects some building to, say, a shoreline of a river, where it's an application type problem, then I would expect an approximated answer. Okay, so again, I don't think we talked about that before, but that's one reason why you might use this type of problem in analytic geometry. So you want to build a road, say from the hospital to the edge of a river, which is represented by a line, and you want to build it so that it's the shortest road possible. Well, that would give you the length of the road that you need to build. Okay, so let's finish off this problem here. So let's do, we've got 10.8 minus 6 all squared, and then we're adding 9.4 minus 19. Whoops, notice I forgot my bracket, so let's put those in. So plus bracket 9.4 minus 19 all squared, and that gives me 115.2. So my distance is the square root of 115.2. I'm not going to approximate it because I want an exact answer. And here they don't give us any units for what each tick on this graph represents, so I'm just going to say it's square root of 115.2 units. Okay, if they were telling me that things were measured in centimeters, it would be centimeters. If they told me it was measured in kilometers, it would be kilometers. Okay, so let's do a quick recap. So step number 1, notice how I use a diagram to help guide me. I don't even bother with an accurate diagram because, again, I'm just using it as a guide. So here we realize that to find this distance, I need to find the point at which the line hits the given line. So in other words, I have to find the point of intersection between the given line and this perpendicular one. I use the fact that it is perpendicular to get the slope of the second line, knowing the slope of the first. Once I find the equation, I'm just left with solving a system of equations to find our point of intersection. And once we have the point of intersection, we can use the distance formula to find that length. Okay, that's it for this one.